Once again, welcome to a new problem. This time we have two columns. One column has to do with steel. It's a steel column that's going up until a specific height, h. So we'll call that h of steel. And then we have another column. We don't know what the height is, but this one also is made of a different material, so height of granite. The steel itself has a density. We're given the density of steel as being equivalent to so rho. Rho is the symbol for density, and the density of steel is equal to 7.8 times 10 to the 3 kilogram meter cubed. The density of granite is equivalent to 2.7 times 10 to the 3 kilogram per meter cube. That's the information we're given. And the other thing that's happening is we want to calculate the height of steel and also the height of granite, the columns. Not just the height, but the vertical height of these two. The maximum height that we can have, maximum height of these two vertical columns without buckling. So buckling is like, when you have a lot of pressure on a column and it starts to wiggle a little bit, okay, because of the stress that it's experiencing. A lot of the stress in the column will happen at the base, and it's going to be due to the weight of the columns. So, if the weights, if the material cannot support the stress, then it's going to buckle. That's what happens. It buckles. The other thing about the problem is that they're asking if the cross-sectional area is independent of the stress itself. So if you think about the cross-sectional area, it's kind of like cutting an orange into two pieces. And so is the now we want to know if the maximum height. So in part A and B, we'll calculate the vertical heights. This is A, or rather this is A and this is B. But then more so, we want to know if the maximum height is independent of the cross-sectional area. That's what we want to know. Think about this as the cross-sectional area. You slice it, and it can happen even at this level where you slice that level, and then you see it. If you look at the cross-sectional area from the top, it becomes circular for this column, for example. So in the next page, we'll start the computation process. We do know that the stress of the whole system in the columns is equivalent to the force over the area. That's the definition of the stress. So in general, the force is being provided by the weight of the columns, which is mg over A. But as a side note, volume or or density, which is rho, is defined as the mass over the volume. So that means if you multiply both sides by the volume, you get to define the mass in terms of the density and the volume. And so we can do that replacement on the mass and say rho v g over the area. So it seems like the weight can also be defined in terms of the density and the volume, just a different way of defining the force that's responsible for the stresses. And then we can go ahead to see that if this is the case, volume is length times width times height in general, thinking about a rectangular shape, for example. So this is the length, the width, and the height. The length and the width is the area itself. So the volume can also be defined in terms of the area times the height. So moving on to the definition we have for this problem, we get to see that if we have rho Vg as the force responsible for the stress over A, we can redefine that in terms of rho. Instead of V, we change the V into A times H, because that's the we derived the volume in terms of the area and the height. And you can see that from this diagram. Times G, and then we have A. These two A's cancel out. So all of a sudden, we have a different definition for stress. So stress becomes equivalent to rho times H times G. And the thing about this formula for stress is that it doesn't have the area. So the new stress formula is independent of the area or the cross-sectional area, and therefore the area does not affect the maximum height. So that's the relationship we have there, because right now we eliminated the area. So going on to the next page, we can also see that the stress will be equal to the compressive strength without buckling. So that's the kind of relationship we have. Rho, the stress is rho GH or rho HG. So rho HG equals to the compressive strength, and we can always think about this compressive strength as being the maximum. So if we have a maximum compressive strength, we also have to think about the maximum height. Max G equals to maximum compressive strength. And this means that we can solve the maximum height in terms of the maximum compressive strength over rho G. So that's what we have right here. So now we have a new definition of the maximum height in terms of maximum compressive strength. So in the next page, we'll do the first one for steel. Under steel, we have maximum height equals to the maximum compressive strength for steel, which is 500 times 10 to the 6 Newton per meter squared. And then we also have rho, which is 7.8 times 10 to the 3 kilogram per meter cubed. And we also have to include the acceleration due to gravity, which is 9.8 meters per second squared. So the only thing we're doing this problem, we're following this formula right here. And when we solve that, we get to see that the maximum height becomes equivalent to maximum height becomes equivalent to 6.5 times 10 to the 3 meters. That's the maximum height for steel before buckling. We could repeat the same process this time to solve the maximum height for granite. We should have called this steel, and then this is granite. The maximum compressive strength for granite is 170 times 10 to the 6 Newton meters squared, all over 2.7 times 10 to the 3 kilogram per meter squared, times 9.8 meters per second squared. And this gives us a maximum height for granite. The granite column is 6.4 times 10 to the 3 meters. So hope you enjoyed the problem. Feel free to send any questions or comments. Just a quick recap. We had 2 columns, one for steel and the other one for granite, and we wanted to find out what's the maximum height before buckling, and that has to be connected to the maximum compressive strength. They both have different densities. Steel has a density of 7.8 times 10 to the 3, and granite has a density of 2.7 times 10 to the 3. And then the stress is defined as the force over the area. The reason why we're using the stress is so that we can come up with a new definition of stress that eliminates the area. And the way to do that was to define mass in terms of density and volume, and then go ahead and define volume in terms of area and height. And so we simplify the problem and we get the stress to be rho hg. And once we've defined the stress, we can equate that to the compressive strength and come up with a formula for the maximum height, which is maximum compressive strength over rho g. And that way we're able to simplify and determine the maximum height for steel, 6.5 times 10 to the 3 meters, and the maximum height for granite, 6.4 times 10 to the 3 meters. Hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day. Okay, thanks. Bye.